In this section, we're going to look at what derivatives tell us about graphs of functions. So in particular, we're going to look at how to determine when functions are increasing versus decreasing. We want to be able to identify local maxes and mins. Without actually looking at the graph, we want to be able to find out if a point we're looking at is a maximum or a minimum for a function. And we want to talk about something called concavity and inflection points. Okay, so to start out, let's talk about what it means for a function to be increasing and what it means for a function to be decreasing. So increasing, well, the idea is easy enough. Let me put it this way, if we move from x1 to x2, so from one x value to another x value, then if the function value above the x2 is bigger than the function value above x1, for all x's, so no matter where we move to the right, if this is true, then we say the function is increasing, at least on some interval I. And then similarly, if we move from x1 to x2, and that is any x1 and x2 in an interval I, if the second function value is less than the first function value, then we say the function is decreasing. So, for example, f of x equals x to the 1/2, meaning the square root of x, well, this function is always increasing. So we could see that looking at the graph. So it is always increasing. We have another way to determine this. That is, if we look at the derivative, so that is noting that f prime of x is 1 over 2 x to the 1/2, and noticing that x to the 1/2 can never be negative, so that means f to the f prime of x is always greater than 0. That means the derivative is always greater than 0, so it's increasing. All right, now if we look at 1 over x, so let's take a look at that graph really quick. And if you notice, as we move to the right, so these are, if we pick an x2 to be further to the right than an x1, then the function value is always less than at the second x, the x that's further to the right. So this is always decreasing. Now, of course, we have a discontinuity at x equals 0, but even if we move past x is 0, the function is still decreasing. And if you notice something about the derivative here, g prime of x is negative 1 over x squared. And of course, for any x that you plug in here, not 0 of course, but any x you plug in, x squared will be positive. So 1 over x squared is positive, which means negative 1 over x squared is always less than 0. So that tells us that it's decreasing. And that's exactly what this test for intervals of increase and decrease is saying. If f is a continuous function on an interval I and differentiable at all interior points of that interval, then if the derivative is greater than 0, then we say f is increasing. And if the derivative of f is less than 0, then f is decreasing. So notice, this does require it to be continuous on an interval I, but the point is, we can consider I to be this interval from negative infinity to 0, not including 0, union, or then separately look at the interval from 0 to infinity. So on either one of those intervals, the function is continuous and it is decreasing. Now if I had to sketch a continuous function satisfying these, Well, let me pull up some paper here. So, give ourselves some graph paper, and let me get those details. So we want the derivative to be greater than 0. That means increasing from 0 to infinity. So, sorry, negative infinity to 0. So, pretend I was drawing straight lines here. That's the point of the graph paper. I'm still getting a hang of this writing utensil though. So I want my derivative to be greater than 0. That means I want my function to be increasing, first of all, on the negative infinity to 0, not including 0. So let me just make some notes, and I might have to come back here and make some changes. But here's the idea. I want to be increasing, and I want to be increasing on the interval from 2 to 7. So let's say this is 1, 2, 3, 4, 5, 6, 7. Now at this point, without looking at the other restrictions, I can pick any point at 2, and I want to be increasing to where x is 7. And notice I'm doing open circles because the interval is non-inclusive, open parentheses. Okay, now I want to be decreasing from 0 to 2, so that's going to fill in the missing gap between these zeros and 2's. I don't know yet what's happening exactly at 2 because notice these are open again, and then decreasing from 7 to infinity. Alright, so I need to be decreasing, and I could pick anything. At this point I might again have to come back and... Oh, you know what? I'm just realizing this is 3, isn't it? So let me come back here and make this change. Alright, and then make that change. Okay, so I want to be decreasing here. Alright, so decreasing 0 to 2 and 7 to infinity. Let me not forget about that one. So, I don't know, let's just pick one here. I get to make this part up. So that is decreasing from 7 to negative infinity. Alright, now my function is undefined. My derivative is undefined. And my derivative at 2 and my derivative at 7 are 0. Okay, so what that means is the derivative at 2 and 2 and 7 are 0. But my derivative at 0 is undefined. So, for example, I could do this. I could say... So at 0... this derivative would be undefined. Alright. But now I have to figure out how do I make the derivative at 2 be 0? Well, with my graph as it is, it won't quite work. I know I need to be decreasing as I come up to 2, and I need to be increasing as I move away from 2 towards the right. But at this point, the derivative looks like it's undefined. However, if I do something like this, so let me make some changes. Get rid of this guy. If I smooth this out a bit, and then make the derivative look like it's 0 there, now, notice right here at 2, it looks like you'd have a horizontal tangent line, and that would give me a derivative of 0. Now I want to do the same thing at 7. I want the derivative to be 0. So let me smooth these guys out here. Also keeping in mind that I want to be increasing the whole time until I get to 7, and then decreasing after 7. So again, here, it looks like I'm going to have a horizontal tangent line. And then I'll be decreasing after that. So now some graph looks like this. Your graph would of course look different because there are infinitely many possibilities, but these are the key pieces that I'm looking for. The horizontal tangent line above 2 and 7, and an undefined derivative at 0. Your undefined derivative could do something like this. Have a peak right here, like the absolute value function. It could be something where your function, oh, and I shouldn't draw my, I'll be a little more careful here. I want it increasing to 0. So an absolute value, maybe a negative absolute value function could look like this. There, your derivative would be undefined. The other possibility would be you could have your function do something like this, go up to infinity. And here on the left, it's decreasing as you approach 0, and it's, sorry, increasing as you approach 0 from the left, and decreasing as you approach 0 from the right. So that would fit the bill. And then if our function had to be defined, we'd just pick a point where x equals 0 for our function to be defined at. Okay, but I think otherwise the function that or the graph that we went with would fit this bill. Okay, so let's find intervals on which the following functions are increasing or decreasing. Come back up. If I wanted to take a look at this first one, 3 cosine 3x. Well, the way to do this is to, on this interval specifically, is to figure out what's the derivative. So let's look at number 1 first. F prime of x is -9 sine of 3x. So just chain rule that. Now what I want to know is, where is this 0? Where is this 0? But also, I want to know where it's undefined, because notice we can change, just like we did here. We don't have to necessarily have the derivative be 0 for our slope to change from negative to positive or vice versa. It could also happen when our derivative is undefined. So I want to know, where is this 0 and where is it undefined? Well, I know sine of 3x, I know sine is undefined. Sine is going to be 0 anytime I have pi or negative pi or 2 pi. So basically any multiple of pi. So when 3x equals some integer multiple of pi, I know that sine of 3x will equal 0. Well, that means x is n over 3 pi. Now, how many of where n is an integer, so how many of those are in this interval negative pi to pi? Well, certainly if n is -3, we get negative pi. If n is -2, that would be in the interval because we'd have -2/3 pi. -1, 0 certainly is in the interval negative pi to pi, because if I plug 0 in for n, I'll have 0 pi. 1, 2, and then 3 would give me 3 over 3 pi, and so that gives me pi. So these are all the n values that would keep x within that interval. So what that tells me is, at those points, those could be where this function changes from a positive slope to a negative slope, or vice versa. Okay, so let me graph these and see what's happening. So if this was negative pi to pi, And I know the slope is 0 at negative pi, let's call this and this negative 2/3 pi, negative 1/3 pi, 0. And this one can be 1/3 pi, and then 2/3 pi. So how do we determine which is which? Well, in a basic function like this, I know how sine acts. It's a sinusoidal graph. So if I can figure out where it's positive in one of them, one area down here, then I know it's negative in the next and positive in the next. All right, so let's see. Maybe I could pick an easy one. How about in here? So I need some value to plug in that is between 0 and 1/3 pi. How about 1/6 pi? I'll do 1/6 pi just to see what the derivative is. And I know sine of 3 times 1/6 pi equals sine of pi over 2. And we know that sine of pi over 2 is 1. But of course, that's not my function derivative. It has a negative 9 in front. So negative 9 times each of these is really my derivative at f prime of pi over 6. And I don't really care that it's negative 9. What I care about is the fact that it is 0. Less than 0, rather. So that means my function is doing something like this. Now keep in mind, this is not the actual function that we're interested in. This tells you what the derivative looks like. So what's important is that you have a positive derivative between negative pi and negative pi, 2/3 pi. You have a negative derivative in the next section, positive in the next, negative in the next, positive, and then negative. So that means your function is increasing wherever your derivative is positive, and it's decreasing wherever your function is negative. So we would say it's increasing on the interval negative pi. Let me erase this. Negative pi to negative 2/3 pi. I'm using the union notation, but you don't have to. If you want to separate these by commas, that's fine. Negative pi over 3 to 0. And from pi over 3 to 2/3 pi. And then decreasing on the others. Okay, so try the same thing with these guys. These are just polynomial functions. One thing to keep in mind about polynomial functions, if you look at the degree of the polynomial, that tells you the maximum number of zeros there are, and one less than that tells you the maximum numbers of direction changes. So that works out because the degree of the derivative will always be 1 less than the degree of the function itself. So for example, f prime of x will be some x to the 4th function. And an x to the 4th function could look at most like this. And so the most number of times it could change from positive to negative is here, 2, 3, and 4. Now that doesn't mean it will change directions that many times. For example, so this is the x-axis. It could be that the x-axis is down here, and the function never actually changes directions from increasing to decreasing or vice versa. So you have to be a little careful. This just gives you a maximum number of possible times it changes from increasing to decreasing. And x to the 3rd, for example, if you think about this, that function looks like this, given the x and the y-axis, but notice it's never changing from increasing to decreasing. And if you think about it, that's because the derivative, which is 3x squared, just looks like this and never goes from positive to negative. It always stays positive, except it's 0 right here at 0, 0. So what I would say is this increases from negative infinity to 0 and from 0 to infinity by looking at the derivative graph. So one thing to note, critical numbers do not always correspond to a local maximum or minimum, and that's exactly what I was saying. So they just help us figure out where they could be. So for example, let me look at this graph. This is the x to the 3rd graph that I was mentioning, and here is x to the 1/3. So in the x to the 3rd graph, the red line here, that's what we just looked at. It does have a critical number where the derivative is 0, but it doesn't actually change from being a positive slope to a negative slope. It continues on being positive. And same thing with x to the 1/3. If you look at 0, 0, the derivative is undefined there, so we would get a critical number. But that doesn't mean that the function actually does change from negative to positive slope. It stays positive. Okay, so this is what we call the first derivative test. Suppose that f is a continuous on an interval that contains a critical number c, and assume that f is differentiable on an interval containing c, but maybe not at c. So it's differentiable around c, but maybe it's not differentiable at exactly c. So if the derivative changes from positive to negative as x increases through c, then f must have a local maximum. So if it goes from negative to positive, because what we're thinking of is your function is doing this, and so at c, it's changing from having a positive slope to a negative slope, that means it must be a local maximum. So the idea, similar idea for local minimum, and then if the derivative does not change sign as x increases through c, then f has no local extrema. And that example is the easy one, is x to the 3rd, which does this that we just saw. The sign doesn't actually change. The derivative sign does not actually change. It goes from positive and then stays positive as we go through 0. So the idea is, if we want to test a critical number to see if it's a local maximum, we can just look on either side and look at the derivative. And if the derivative on the left is positive and the derivative on the right is negative, then we know we have a local maximum. But if the derivative on the left is negative and the derivative on the right is positive, we know we have a local minimum. So let's try this. On this number, this first example, where f of x equals 2, x Let's get rid of that. 2x to the 5th minus 5x to the 4th minus 10x to the 3rd plus 4. Well, let's calculate the derivative. 10x to the 4th minus 20x to the 3rd minus 30x squared. All right, so I want to know, where is this 0 on this interval? Well, certainly it's going to be 0 at 0, because we can factor, and I'm going to go ahead and take a 10 out of here also. 10 and an x squared out. That leaves me with x squared minus 2x minus 3. Okay, so let's figure out, so we get 0 from this, and that is definitely in the interval. There may be another critical number in that interval, so let me try to get that out of here. So I want to figure out, where is x squared minus 2x minus 3, 0. Well, does that factor? It looks like we could factor it as x minus 3, x plus 1. And so the x values that we get from here are either 3 or negative 1. All of which are in the interval here. Negative 1 is in there, and 3 is in there. Okay, so let's see what happens in each of those situations. So keeping the factored version, a lot of times this is easier to see what happens to the left or right. So f prime of x, let me look at 10x squared, x squared minus 2x minus 3. And one thing to note is I don't actually care what the derivative value is. I just want to know, is it bigger than 0 or less than 0? And that'll tell me increasing or decreasing. So I'm actually going to ignore this positive 10, because that is not going to change the positive or negative polarity of the derivative. So when I plug things in, I'm just going to plug it into the rest of this. The 10's just making it bigger, but it's either going to be a bigger negative or a bigger positive. Okay, so what I want to do is, on my interval between negative 2 and 4, I'm going to split those up over the critical numbers. So I know 0, I know negative 1 is a critical number, I know 0 is a critical number, and I know 3 is a critical number, because those are all what make the derivative 0. And we should also look at where the derivative is undefined, but again, we're looking at a polynomial here. Okay, so let me plug in a number that is maybe a little bit less than negative 1. So for example, 1/2. Negative 1/2 rather. And I should be even more careful because I'm over here, so that means I'm plugging in, let's try negative 3/2. So f prime of x in x squared, x minus 3, and x plus 1. Now, these guys are always positive, so I'm going to ignore these altogether. If I plug in negative 3/2 here, I get a negative. And if I plug in negative 3/2 here, I get a negative. So that tells me this, to the left of negative 1, is going to have a positive slope. And if I go to the right of 1, negative 1, so plug in, say, negative 1/2. So let me keep this straight. This is what I got when I plugged in negative 3/2. Now I'm plugging in negative 1/2, but I'm going to get a negative here and a positive here. So this derivative is negative. And now if I plug in, let's go, I don't know, how about plug in 1? So if I plug in 1 into here, I'm going to get negative and a positive again. So again, this is negative. And then over here, if I plug in, say, 3.5, well, now I'm getting positive. Oh, let me keep track. This was plugging in positive 1, and this is plugging in positive 3.5, let's say, and a positive. So this is positive. So that means on this interval, what's happening is, let me redraw it down here. So this is 4, this is -2. Here's -1, where I know my derivative is 0, and here's, let's see, 0, and here is 3. So now at each of these points, the derivative is 0. What's going on is that somewhere, I don't know where it is on the y exactly, but my function has a positive slope, but levels out at -1, and then starts going negative because I have negative slope here. Then, because the derivative is 0 again, it must level out again as x approaches 0. However, because my function stays negative, I should be more careful, because the slope stays negative, it keeps going down like this, and then levels out where x is 3, and then starts going up again. Alright, so that's what I'm able to get from the first derivative test.